Hello everyone and welcome back. My name is Mr. Koval, and in this video we're going to go over some practice problems involving calorimetry. So the thing I want to remind you of is that when we're talking about calorimetry, we're talking about the transfer of energy or heat from one object to another within a system. And so what that means is that when we're talking about the system, we're referring to the objects themselves that are involved in the heat transfer. Anything outside of that is considered the environment, and so we're not going to pay attention to that. So, for example, if you have a block and you're putting it in water, right, a hot block putting in cold water, the block and the water are the system. Anything outside of that would be the surroundings, right? So here we're understanding that the according to the first law of thermodynamics, heat is not created nor destroyed. So when we are looking at the whole system, then the change in energy is zero in the sense of there's no loss of energy in the system. We just have it transferred from one place in the system to another place in the system. So from the block to the water, or from the water to the block, or whatever your system is made up of. Okay, and so I would just want to recap that before we start on these problems because that's going to come out and that's going to kind of explain the math a little bit. Okay, let's talk about problem number one. So problem number one is calculate the specific heat of a metal if 2.36 times 10 to the 2 grams of that metal at 99.5 degrees Celsius is added to 125 milliliters or 125.0 milliliters of water at 22.0 degrees Celsius. The final temperature of the system is 25.4. So what they mean by final temperature of the system is that both objects in the system, the metal and the water, have reached the same final temperature. So the final temperature of both the water and the metal are at 25.4 degrees. So that's their final temperature. So how do we figure this problem out? How do we find the specific heat of the metal or anything in this problem? Well, the first thing we have to understand is that the heat lost by the metal, right? So if the metal starts at a higher temperature, so if it's now going from 99.5 degrees Celsius, now it's down to 25.4 degrees, so the metal lost energy. That energy lost by the metal was picked up by the water. And so outside of that, none of the heat was lost. We're assuming that it's not lost to anything in the environment, it's not absorbed by the container, it's not lost to the air or anything like that. So it's just contained. So there's no loss of energy of the system. so so we represent that as, remember, Q1 is equal to the negative of Q2. And remember, this negative means the opposite of, right? So whatever this amount of energy that's gained by this part of the system is lost by this part of the system, right? So we can use this equation, or we can use this equation. It's the exact same equation, but written out differently. So, but they mean the same thing. So you could use either one to solve the equation. I'll do probably each one at least once in the practice problem so you can see how it's done, but it's pretty much the exact same thing that you're doing. Now, since I'll start with this form here. So I'll do, for this problem, I'll do this form. And then for the next problem, I'll do this one. So remember, when we have our Q values, we have the Qmat, or QMCAT, I should say. Q is equal to mass times specific heat times delta T, the change in temperature. So we are going to need one of these for each of the problems. So instead of maybe Q1, Q2, we could call it QM for the metal and QW for the water, the heat that's lost by the metal and the heat that's gained by the water. Now, which side is water and metal? It doesn't matter because the math will work out exactly the same. The only thing you need to pay attention to are your negatives. So if you have a double negative, you got to make that a positive. So you really got to pay attention to your negatives in the equation. And so you got to remember, whichever side is losing energy, you're going to end up with a negative magnitude of the energy on that side. But no worries, it's the negatives and all of the math should work out. So regardless of what equation you use and regardless of what side you put water and metal on. So I could put water on this side and I could put metal on this side. It would not matter for the calculation as long as you're consistent with your math and where you're putting your data. Okay, speaking of data, the thing you want to do is start listing out the information they give you and labeling it so you know what it is, right? So let's start with specific heat of metal, and they give us the mass of the metal. So the mass of the metal, we'll say M is the mass of the metal. So mass M sub M is 2.36 times 10 to the 2 grams, okay? And the initial temperature is 99.5 degrees Celsius. So TF of the metal is 99.5 degrees Celsius, okay? So that's what we have so far. And the specific heat of the metal, we don't know. That's what we're trying to find. Okay, now what about the water? So we're told that we're given 125.00 milliliters of water. So we have to remember that the density of water is 1 gram per 1 milliliter. So 1 gram of water is equal to 1 milliliter of water. So 1 milliliter of water is equal to 1 gram of water. So if they give you milliliters of water, you can just convert that to grams right away, because it's the same thing. So mass of the water, mass W, is going to be equal to 125.0 grams. Okay, and then we have the initial temperature of the water. So we have T initial of the water, that's going to be 22.0 degrees Celsius. And again, the final temperature of the water, TFW, is equal to 25.4 degrees Celsius. Now, the other thing that you need is the specific heat of water. So this is something either given to you or you'll have to look it up. So the specific heat of water is 4.18. We'll use that one. So the specific heat of water is 4.18. Sometimes I believe they put a 4 there too, but we'll shorten it to 1.8. So 4.18 joules per gram per degree Celsius. So I'll put a line here to kind of separate. So we have the information. Oops. I put the line in the wrong place. There we go. So we got our information for the mass of the metal, or the metal. We have our information for the water. Now we can set up our equation. So we're going to use this one here. Now QM, we're going to use this equation for the metal. So QM is equal to negative QW. So Q is equal to this. So we're going to replace this. We're going to substitute this in for Q. So here, so we're going to have mass. So this is the metal side. So we're going to have the mass of the metal times the specific heat of the metal times the change in temperature of the metal. But I'm going to write it out because we have different temperatures. So we have T final minus T initial. And this is of the metal. And this is equal to QW. So it's going to be negative. And then everything inside, we're going to then use the same equation here for the water side. But everything's going to be in terms of water. So the mass of the water multiplied by the specific heat of the water multiplied by, and again, we have T delta E. So I'm going to change this to square brackets. So final temperature of the water minus initial temperature of the, oops, let me fix this so you can see it. There you go. Okay, so the Q side of the metal side is equal to the negative of the water side. Okay, so now all I need to do is plug in the values here and solve for the missing piece, which is the specific heat of the metal. So the mass of the metal, that's going to be 2.36. So 2.36 times 10 to the 2 grams. And the specific heat of the metal is something we're looking for. We don't know. And then we put in final temperature minus initial for the metal. So the final temperature is 25.4. So 25.4 degrees Celsius minus the initial temperature, which is 99.5 degrees Celsius. And we do the same thing for the water side. So the water, we have 125 grams. So we're going to, don't forget your minus. So we have 125.0 grams of the water multiplied by the specific heat of the water, 4.18. So 4.18 joules per gram degrees Celsius, and multiplied by the temperature change, which is final minus initial, 25.4 degrees. So 25.4 degrees Celsius minus initial temperature, 22.0 degrees. So 22.0 degrees Celsius. Oops, let me fix that. There you go. So now I have it set up with the numbers. And so now all I need to do is just calculate and solve for the specific heat of the metal, right? So, and then everything should cancel out. So if I do the calculation, right, if you do the calculation right, then you multiply both of these together. So figure this out. Notice that this is going to be negative because I'm subtracting a larger number from a smaller, so that should be negative. And then so then this side will be negative, and we have a negative on this side, so the two negatives are going to cancel out, and so both sides will be positive, and so you should end up with a positive specific heat. So let me calculate that really quick and give you your answer. Okay, so I've calculated the answer on this side here. So if we do the calculation, you'll note it's 1,776.5. Now, one of the things I want to point out is notice you want to pay attention to your units and see what cancels out and what you're left with. And what you're left with should match with what you're trying to find. So if you notice here, grams will cancel out with grams. And then degrees Celsius here will cancel out with degrees Celsius, and you're left with joules. So on this side, we end up with a negative, and it's 1,776 joules of energy. And then on this side, notice you have grams and you have degrees Celsius. You're going to divide this side by both of these and then divide it here, so you'll end up with joules over grams degrees Celsius. So that's what you would expect if you're solving for specific heat, which is what you're trying to find. So the units work out, so that makes sense. It seems like we set up our equation correctly and we're solving it correctly. So then when you divide both sides by these, you end up with a specific heat of 0.102 joules per gram degrees Celsius. So that's what you should get when you finish the calculation. To figure out what this is, multiply these together and then divide by that. Now this should be a negative, so when you divide by negative, it turns positive. So your specific heat should be positive. So that's problem number 1. I hope that was helpful. Let's look at problem number 2. Okay, welcome back to problem number 2. In this one, I'll go a little bit more quickly since we've already familiarized yourself with the process in the first one. It's the exact same process for any other problem. So in this problem, I'm going to use this form. 0 is equal to Q1 plus Q2, or in this case, the metal and the water, right? So here's our problem. We now have a lump of chromium and it has a mass of 95.3 grams and is at a temperature of 90.5 degrees Celsius. It is then placed into a calorimeter, which already has 75.2 milliliters of water in it, and it is at 20.5 degrees Celsius. After stirring, the final temperature of the water, the chromium metal, and the calorimeter is 28.6 degrees Celsius. What is the specific heat of the chromium metal? Okay, so in this case, they're throwing in the calorimeter. Sometimes the problem will require you to factor in the amount of heat absorbed by the calorimeter. You would have to be given the specific heat of the calorimeter, the mass of the calorimeter, and all that stuff. But they're not giving us this information. So the assumption is that the calorimeter is not absorbing any of the heat from the transfer. So the calorimeter is really not actually part of the system. So we're ignoring that as not absorbing anything. Or if it is part of the system, it's not really interacting with the process. So there's no absorption or loss of heat by the calorimeter. So we're going to ignore that in our calculations. Of course, if we did have to consider the calorimeter, then that would be a third Q in our equation. It'd be Q1 plus Q2 plus Q3, and the Q3 would be the heat absorbed or released by the calorimeter, most likely absorbed by the calorimeter, and so you would have to be given information. But again, all that means is that you would require another Q equals MC delta T for the calorimeter, and it was just another extra thing to add to the equation. But solving it is not any more difficult, or it's not different from what we're going to do now. So 0 equals Q1 plus Q2. So the loss of energy, the difference in energy during the process of the system is zero. There's no change in the total energy of the system because there's no loss or gain of heat by the system. There's no creation of energy or destruction of energy during this process. So the change is going to be zero. So these two should add up to zero. Okay, and we saw that before because remember the magnitude should be exactly the same because you're transferring energy from one to the other and it's the exact same amount. It's just that one is going to be negative because it's absorbing, it's releasing energy, and one's going to be positive because it is gaining the energy. Okay, so let's go ahead and list our information. So we'll start with the metal. So we'll call Q1 metal, Q2 will be water. So what's the mass? The mass of the metal. The mass of the metal is 95.3 grams. What's the initial temperature? So the initial temperature, or we'll write, let's do specific heat of the metal. We don't know the specific heat of the metal. That's what we're trying to find. The initial temperature of the metal, that is 90.5 degrees, 90.5 degrees Celsius. And the final temperature of the water is what this is, so 28. So we have final temperature of the metal is equal to 28 degrees, or 28.6, sorry. So 28.6 degrees Celsius. So that's everything for the metal. What about the water now? So the mass of the water. So as we were told before, the milliliters, the volume of the water is going to be the same as the mass in grams because the density is 1 gram per milliliter. 1 gram is equal to 1 milliliter of water. So if we're given 75.2 milliliters, that's the same as grams. So 75.2 grams of the water. And we're given, again, our specific heat of the water is the same as before, 4.18 joules per gram degree Celsius. Our initial temperature of the water is 20.5 degrees Celsius, so 20.5 degrees Celsius. And then our final temperature of the water is the same as the final temperature here, 28.6. So 28.6 degrees Celsius. Okay, so we've got our information. Now we just plug it in. So our formula now, if we replace these with this part here, then 0 is going to be equal to, for QM, it's mass of the metal multiplied by the specific heat of the metal multiplied by the change in temperature of the metal, plus, again, it's going to be the same for the water. The mass of the water multiplied by the specific heat of the water multiplied by the temperature change of the water. So now all we do is just plug in everything we know. So I'm going to start over here to give myself some space. Okay, so the mass of the metal, so this is going to be 95.3 grams. And then we have our specific heat of the metal, which we don't know. And then our change in temperature. So you can calculate the change in temperature here, or just plug it in, final minus initial, and then do it later. It's up to you. I like to write it out. So final temperature of the metal is 28.6 degrees Celsius minus the initial temperature, which is 90.5 20.5 degrees Celsius. Okay, so this is our metal part. Now we'll do the water part. So we just plus, and then we do the water. So it's going to be the mass of the water, which is 75.2 grams. 75.2 grams multiplied by the specific heat of the water, which is 4.18 joules per gram degrees Celsius. Okay, and then we have our temperature change, final minus initial. So let me turn this a little bit to give some space. So final is, again, 28.6. So that's going to be 28.6 degrees Celsius minus final minus initial, and the initial is 20.5 degrees Celsius, so 20.5 degrees Celsius. So we've added all our information. So now all you need to do is multiply and divide and rearrange this. So notice that this cancels out, right? So grams cancels out with grams, degrees Celsius cancels out with degrees Celsius. You're ending up with joules on this side. So on this here, you have joules. And then here, you're going to have grams multiplied by degrees Celsius. So let me calculate this out a little bit, and I'll show you what I got. Okay, welcome back. So now that I have done my calculation, so what I did here is I calculated all this, I multiplied all this, and so I got 25.46.1216 joules, right? Because grams and degrees Celsius canceled out, leaving me with joules. So I got this many joules plus, then I calculated the the temperature change, which is negative because I'm subtracting a larger number from a smaller number. So this is going to be negative, which is what gives me the negative here, and I multiply by 95.3 grams. So then I get on this part here 5,899.07 gram degrees Celsius. So I get this. Now these are added together and they equal to 0. Now I want to solve for, oops, I forgot the specific heat of the metal. So this multiplied by the specific heat of the metal plus this should equal 0. So now all I'm going to do is I'm going to bring this to this side. So then if I bring this over here on this side, it's going to be positive 5899.07 gram degrees Celsius multiplied by the specific heat of the metal equal to positive 2,546.1216 joules. So to solve for the specific heat, I just divide both sides by this, and then I end up with joules over gram degrees Celsius, which is what I would expect for the specific heat of the metal or specific heat in general. So when I do that, I get a specific heat of, give me a second, I get an answer of 0.432. So the final answer is going to be 0.432 joules per gram degrees Celsius. And so that is the specific heat of the metal chromium. Okay, so let's go to practice problem number 3. So that's going to have to be in another part of the video. So please make sure that if you like this video, hit that like button, share the video with your friends, subscribe to my channel, hit that notification bell, and also hit the all so you can be notified by all the videos I put out. And also put a comment down in the comment section below. Let me know what you think, and let me know if you have any questions. I'd love to hear from you. Thanks for joining me, and I'll see you next time. Have a great day.